We review the 3 revision sheets. Guys, okay, Hani, guys, now we're going to start a new topic in physics, and that's dealing with sound. So I'm going to explain to you why do you hear me now, and how can we describe a sound wave. And we're going to talk about a very interesting phenomena in physics and then sound. Actually, it's valid for any waves, and that's Doppler effect.
Doppler effect?
Yes. Yes. And we're going to study many applications for Doppler effect. This is the most used phenomena in physics, actually in science in general. It has lots of applications. So sound wave. Sound wave are longitudinal wave. Longitudinal wave, does that mean that we have a wave that's transverse wave? The answer is yes. We have 2 kinds of waves. One of 2 kinds of waves, one of them we call it longitudinal wave, and the other one we call it transverse wave. The difference between them simply is if the propagation of the wave, if the wave propagates and transfer energy in the same direction, we call that longitudinal wave. For example, sound wave. When I stand here and I talk, you guys hear me. So actually what happens is air in front of my mouth, in front of the sound source, vibrates with the voice, with the energy comes from the sound source. And that vibration, air molecules in here, it collides with the adjacent air molecule and makes that vibrate, and it collides with the adjacent air molecule and makes that vibrate. So the energy is getting, the sound is propagating in that direction, the wave is propagating in that direction, and the energy is also transferred in the same direction. We call that longitudinal wave. On the other hand, we have another kind of wave which is not the sound wave, that's the transverse wave. And a good example of this, if you have a rope and if you shake it, then you find a wave in it. We call that kind of wave a transverse wave. Another kind of wave that we all see in the stadium, the people when they make this human wave in the stadium, that's another wave. And this is a transverse wave. Why? Why is it transverse wave? Because you see the wave is propagating in that direction around the whole stadium, and the people, the particles, the people, they move up and down. The energy moves in that direction, while the wave is propagating in the perpendicular direction. We call that transverse wave. That's what? Both waves, either longitudinal wave or transverse wave, they have those crest and thrusts. They have a valley and a hill. That's what I call them. A minimum and a maximum. But we're getting there. What I'm more interested in is you look at the people, they move up and down. So that's where the energy gets transferred. And the wave is propagating in the perpendicular direction, and we call that transverse wave. In here today, we're going to concentrate only on sound wave, which is longitudinal wave. So, and we need medium for that sound wave to propagate. So if I talk now in vacuum, you will not be able to hear me. Because as I explained now, the sound needs medium in order for the sound to propagate in. The sound, which is the pressure wave, it makes the medium oscillate, particle oscillate, and collides with the adjacent particles, and that's how the wave gets transformed from a point to another. Minna?
Does that mean that if we're in vacuum or space, we will not hear it?
Yes, that's why we carry that experiment in high school. The teacher got you a bell and put that into a jar and filled the jar with air, and he made the bell somehow to ring, and you can hear the sound. And if he put a vacuum pump and pulled the air out of that bell jar, you will not be able to hear the sound. So we need medium in order to hear the sound. And sometimes when we were young, maybe we read in a story or we tried it ourselves, you can hear the train coming from far away. If you put your head on the railway, you will hear the wave travel on the railway before you hear it in the air. Just do not forget to get away from the train, though. Why is that?
Because the molecules in the metals are closer.
Because molecules, we said, I just explained that, right? We just explained to you how sound wave propagates. What happens is particles oscillate. That's Ali. Then he collides with the second particle, and the second particle oscillates. Then he collides with the third particle, then the third particle oscillates, and the wave gets propagated. It propagates till it reaches the end. So if the distance between those two particles is smaller, the chance that they will collide faster will increase. So actually, by that theory, we can say that since solids has atoms closer to each other or molecules closer to each other than gases, then the propagation of the sound in solids will be faster than the propagation of sounds in air or gases. The math that describes any sound wave, it's simple to a simple harmonic motion. So what happens if I tell you, can we describe the motion of that particle?
Of the motion, vibration.
It's an oscillatory motion. Simple, like it's like Mason spring system that we have explained on Monday.
But it's the same fade away if the air resistance or something.
Yeah, well, that's true. But if we ignore that, if we ignore the air resistance or the resistance to the motion, then that particle will oscillate forever. So for simplicity in this level of the course, we ignore air resistance. But that particle will move in a wave, as a sine wave, like the same wave that we have wrote like last time. So if I want to describe the motion of that particle, I will say that the particle will move with a distance s around a certain position or around equilibrium, and that s will equal to maximum s, maximum displacement, I called it A last time, times cosine omega t plus phi. It's similar to the equation of a mass that's attached to a spring. So the motion of only one single particle that carry the wave can be described by that equation again. If I want to actually divide the sound wave into types, I will divide them into three types. Audible voice, audible wave, that's what you hear right now. This is the wave that we can hear. And that goes from 20 hertz to 20 kilohertz. We cannot hear, our ears are not sensitive below 20 hertz, so anything that has a voice that produces wave with a frequency less than 20 hertz, we cannot hear it. Any source that produces wave with a frequency more than 20 kilohertz, we cannot hear it. Okay? That's why we call that range audible wave. 20 hertz, what's 20 hertz? That's the frequency of the wave. What does the frequency of the wave mean? Number of the oscillation per second. And we have an infrasonic wave, anything that's below 20 hertz. Any vibration that's below 20 hertz, we call it infrasonic, and any vibration that's more than 20 kilohertz, we call it ultrasonic. And we use that ultrasonic in diagnosis. At the doctor, you go to do an ultrasonic. All what he has is a probe that he puts it on your body, and that probe produces an ultrasonic wave, and it gets reflected by your inner organs, and he measures that reflection. Then he can diagnose or can actually map whatever is inside. And this is not only used in medicine; it's also used in engineering. If we want to measure the flow of oil in an oil pipe, we use the same technique. If we want to measure the welding in oil pipe, we use the same technique. We use an ultrasonic wave. Okay, guys? Yes, Ali.
Infrasonic is the same as subsonic, right?
No, subsonic that's the same as ultrasonic.
Subsonic is the same as ultrasonic?
No, subsonic, yeah, that's less than 20 hertz.
Yeah, is that the same as infrasonic?
Yes. Ultrasonic, that's more than 20 kilohertz.
It doesn't hurt our ears.
No, no. Actually, what hurts our ear more is the amplitude of the sound, not the frequency. And we'll talk about that. There is a nice graph in here that I'll show to you in a minute. Oh. Okay. How can we measure the speed of the sound in any medium? The speed of the sound of any medium depends on two quantities: the elastic property of the medium and the inertial property. In more actually scientific way, it depends on bulk modulus, and that's what we talked about in chapter 12, and the density of the medium. This is an empirical equation. That means that empirical equation means that we got that by experiment. There is no actually mathematical proof behind it. V, the velocity of the wave in any gas, equal to the bulk modulus of that gas divided by the density of that gas under the square root. And if we're talking about the propagation of sound wave in solids, V will equal to Young modulus divided by rho under the square root. What is Young modulus? Stress over strain. What does that mean?
Deformation per unit length.
Yeah, what happens is any material can stand a specific load in it. After that, it gets deformed forever. And we have several types of deformation. Elongation, or you change the shape, or you compress it. If you compress it, we call that bulk modulus. It can stand specific pressure. If you deform it, if you twist it, we call that shear modulus. And if you stretch it, we call that Young modulus. And Young modulus measures mainly stress over strain. Stress, that's force divided by perpendicular area, and strain, that's the change in the length divided by the original length. And if we talk about shear, force divided by area divided by shear strain, and shear strain, that's the change in an angle, delta theta. And if we talk about bulk modulus, again, bulk modulus, it's force divided by area divided by the strain, bulk strain, and the bulk strain in that case, that's the change in the volume divided by the volume. And since this is a compression, then the change in the volume will be always negative. That's why we put a negative signs just for convenience.
Okay, that's not different. Why, when we use Young modulus,
Here for solids, this is for solids, mainly for, and this is for gases. Okay. Does the sound velocity change with the temperature? So if I increase the room temperature right now, will the velocity of the wave in the room will change? Before I answer that, let's say that the velocity in air is 334 meter per second. 334 or 331 meter per second. This is a constant at room temperature. Actually, if we, it's 334 at room temperature. It's 331 at 0 degrees Celsius. 0 degrees Celsius. So now, it depends on the temperature. So I'll actually, I'm going to ask you to calculate it, or I'm going to give it to you as a constant. Anyway, in this formula, that formula says that the velocity of the wave actually will increase if you increase the temperature. That's what that equation says. If we think about the physics behind it, assume that we are particles in that room. If I increase the temperature of the room, what's going to happen to those particles? They will start to oscillate. Which means that the chance that they collide with the adjacent particles will increase, which means that the velocity of the wave will increase as well. Okay? So the velocity of the wave will equal to 331 meter per second times the square root of 1 minus T, the temperature, divided by 273. Yes?
But when we decrease the temperature, the particles are very close to each other.
No, when we decrease the temperature, without changing the phase, means that air stays air, then actually the particles do not oscillate. They stay still at their position. They do not move. When you increase the temperature, the particle will start to oscillate around the around equilibrium position. They oscillate around a specific position, so they have the chance of colliding with each other more. Okay, Nada?
I can't understand the relation between the velocity of the sound and the temperature.
Assume that now those are the particles in the room. We're going to heat the room. So that particle will start to oscillate. This is what happens. When you heat the room, temperature of the particle will increase, their kinetic energy increases. You're giving energy in the form of heat, and then transforming that energy into kinetic energy. So that particle will actually oscillate. So now instead of having that location, its location will be from here to there. So the chance that he's going to collide with the adjacent particle will increase. And if it collides faster with the particle, the velocity will increase. That was just an example, guys. Forget it. Or actually read it. It's very straightforward. I'm not going to waste time actually telling you that in class. Now we talked about the frequency range. We divided the sound wave into 3 types according to their frequency range. But actually some other physical quantity that we should be interested in is the amplitude of the sound wave. I can talk to you now with a low amplitude sound, or I can raise my sound. This is the amplitude. The frequency distribution of my voice did not change. It's the same. I just lower my sound or actually increase the amplitude of the sound. This is the amplitude. So the amplitude of the sound, or we call it the intensity, or actually in other way we call it the intensity, intensity of the sound, it's the pressure produced by that sound divided by the area. It's actually, it's the pressure. It's power divided by area. Forget that.
The amplitude is the power divided by
I is the average power divided by area. Any sound source produce, it has a power. It's an energy per unit time. This is an energy. I transfer that energy into the air. So any sound source has a specific power. Power is mainly the energy produced by the source over a short period of time. That's the power. If you divide that power by the area of what? That's very important. You get what we call it the amplitude. Area of what? If you have a point source that produces sound, how will the sound propagate? As a sphere. It propagates in all directions, and it propagates as a sphere. So what will be the the intensity of the sound? This is the sound source somewhere in here. What will be the intensity of the sound at that location? At that sphere, the intensity of the sound is going to be the same, which is the power produced by the source divided by that area, surface area of the sphere, which is 4 pi r squared. So it's the power divided by 4 pi r squared. Mahmoud, are you okay? You want to go freshen up and come back? Okay. Usually that amplitude, that intensity of the sound, that's huge. It's a big number. And actually, in order to measure, if I tell you guys, do I talk with a loud voice right now, or is it not that loud? What would be your answer? Ali? It's not that loud. Heidi? It's normal. It's relative. Hassan is saying it's relative. It's going to be different from one person to another. So actually, in order to accurately measure the intensity of the sound, we have to measure it relative to something else. So we choose another intensity, and we're going to call it the threshold of hearing. This is the intensity that this is the minimum intensity of the sound a normal human being can hear. I0 is the normal, is the average intensity that a normal human being can hear.
Is
And what does a normal human being that mean? Scientists did statistics. They collected a huge number of people and tested them from the age of 20 to the age of 40, and they measured what is the threshold of hearing for them. What is the lowest intensity that they can hear? And why from the age of 20 to the age of 40? Because before the age of 20, our hearing system is not mature enough. It keeps changing. And after the age of 40, our hearing system starts to actually change. And actually sometimes you can feel that in old people, they do not hear really well. So that's why the scientists choose people from the age of 20 to the age of 40, and they made the statistic, and they found out that the lowest intensity of sound that they can hear is 1 times 10 to the power minus 12 watt per meter square. This is I0. So that number is constant. So now if I ask you guys, do I speak with the high amplitude sound or not, you have to divide that, the intensity that comes out from the source, divided by I0, and look at this. And when we do this, we get, because I0 is very, very small, we get a huge number, very big number. So we have to convert that into logarithmic scale just to actually for convenience. So we converted that I over I0 to logarithmic scale and we multiplied by 10, and we call that the beta, which is the sound level, the sound level. So now if I tell you beta has a unit of decibel. So if I tell you that beta is 10 decibel, is that high or is that low? We'll see. We'll see. Is it high or low? We'll see. This is a table that shows us beta for different sources. Beta, threshold of hearing, is 0. How come it's 0? Because we said that beta equal to 10 times log I over I0. So if you put I equal to I0 over I0, that's 1, log 1 is 0. 0 times anything, you get 0. So the threshold of hearing as a sound level, that's 0. Yes. Sure. What we did is, did anyone copy those? Did you copy those, guys? Okay. I said that, let's assume that the psi equal to I0. So what is that on the sound level scale? We said that beta, which is the sound level, equal to 10 log I over I0. So it's 10 times log I0 over I0. If you take I to be I0, I naught, then this is 1. Log 1, which is, this is 1, this is 10 to the power 0, guys. 1 is just nothing but 10 to the power 0. Log 10 to the power 0 is the power, is 0. So this is 0. So you get beta equal to 0, and that's what you see in here. The threshold of hearing is 0. If you whisper, if I whisper to you right now, this whispering sound is 30 decibel. Normal conversation, when you talk in class, that's 50 decibel. When I actually talk to you, when I lecture to you, that's something between 60 and 70 decibel. Vacuum cleaner, that's 70, produces 70 decibel, that's loud. Traffic, busy traffic, not in Cairo, of course, that's 80 decibel. Subway or power mower, that's 100 decibel. Rock concert, that's 120 decibel. If you go near a jet airplane, you get something like 150 decibel. That's why when you go and travel, you see the people that go close to the airplane, they wear that hearing mask. Because the 150 decibel can actually hurt them. So they have to reduce the amount of sound that goes to their ears by wearing those hearing masks. So I'm going to go back, but for a minute, but I want to show you this curve here. This is one of the very nicest curves that I have ever seen. This describes to us the frequency on the x-axis and the sound level on the y-axis. The white area, Heidi, this is general information guide. This is not going to be in the exam, but it's a very nice general knowledge for you. The white area is our hearing. This is what we hear, that white area. So we hear from 20 hertz up to 20 kilohertz. This is the range that we hear in. But at 20 hertz, you need a very high amplitude sound so you can to hear it. So if there is a sound source now that produces 20 hertz, you need it to be very loud, almost 110 decibel, for us to hear it. So our ear is not that sensitive in that area. But look at that area, somewhere from 100 hertz to 8,000 hertz. That range. Our ear is very sensitive. We can hear really well in that range. But if you go to 20 kilohertz, you need a high amplitude sound again, almost 40 decibel to hear it. So that's the white area. Bats, they produce somewhere in the range of sound level of 40 decibel and frequency range more than 20 kilohertz. That's why we do not hear them. Yes?
How can you differentiate between the high frequency level and the low frequency level from here?
It's really hard. Frequency, sharp sound, that's high frequency. That's low frequency. Okay?
But don't they have the same frequency?
No. When I talk now, if I take my voice to a microphone and put it in the oscilloscope, you'll find all the components in that range. There will be some dominant frequencies. That's why my voice will be different than some other people's voice, because there is a dominant frequencies in my voice, but you'll find all the range there. Again, high frequency, that's sharp, very sharp sound. Okay? And low frequency, that's, how do you call it? Rough sound. Okay? Rock concert, that's 120 hertz. Look at this. At 120, there is very important information that we should be aware of. That's the threshold for pain. If you listen to something that's 120 hertz, you will feel pain in your ear. Beyond that, your ear might actually bleed and you might lose hearing. It will bleed and you might lose hearing if you have a sound level more than 120. That's why sometimes in wars you find soldiers that they lose hearing, because if there is something that explodes near to them, with the sound level of 160 decibel, actually they lose hearing if they actually get exposed to that sound level. Ali.
We can hear the early spectrum of the song.
Of the what?
The
Yeah.
can you hear
In the sonar, yes. It's very high frequency.
Hear it?
Yeah. Some old types of them, you can hear them. But now, more of them, they go to higher frequencies.
I have a question. I love thunder. It sounds rough. It sounds quiet.
That's why it's very low frequency.
Low frequency and rough.
Rough sound.
Low bass.
Yeah, yes, exactly like in the bass.
Oh.
Okay? Yeah. Yes? Okay? Nice. So let's go back. This is a nice curve. Actually, if I just want you, each one of you, to spend like 5 to 10 minutes looking at that curve and actually looking at all the information there. It's nice. It's a very nice general knowledge. So let's go back a bit and back, not forward. Okay. So let's assume that what is the sound level that corresponds to an intensity of 2 times 10 to the power minus 7 watt per meter square? What is the sound level that corresponds to a sound intensity of 2 times 10 to the power minus 7 watt per meter square? How to solve that problem? We need to find beta that has an I equal to times 10 to the power minus 7 watt per meter square. Simply plug in the values. So, we have only Doppler effect and that's it. So simply plug in the values. So what I'm going to do, I need to find the sound level. It's 10 times log of 2 times 10 to the power minus 7 watt per meter square. Ahmed, divided by the threshold of hearing, that's 1 times 10 to the power minus 12, and this is going to be 10 times log 2 times 10 to the power 5, and if you calculate that, you should be able to find the sound level in decibel. So that's the sound level. Now, if I tell you this, Sharif is talking during the lecture with the sound level equal to 70 decibel. And Minna is also talking with a sound level equal to 60 decibel. So at my location, I hear Minna talking with a 60 decibel, while Shireen is talking with 70 decibel. What is the sound level at my location? Yes. We cannot add quantities on the Lego scale. I cannot add 60 decibel and 70 decibel and say this is 130 decibel. This is wrong. I should find the intensity level of Minna, then the intensity of Sharif. So I should reverse that equation. So I should put here 70. That's for Sharif. Then find I for Sharif. And I should put 60 for Minna. Then find the intensity for Minna. Then add the two intensities and put them back in that equation to find a new sound level. And you're going to find a problem in the assignment about similar to this. Okay, guys? Doppler effect. What is Doppler effect? Doppler effect says that now we have a source of the sound and we have an observer. I'm the source now because I'm the only one talking, and you are the observers because you are listening to that, you are detecting that signal, that wave. Right now, the sound source, that's me, and the observer, that's Ali, for example, are at rest. No one of us is moving. Both of us are at rest. So whatever I produce, whatever frequency I produce, Ali actually detects. If I produce a frequency of 10 Hertz, Ali will detect 10 Hertz.
No.
Excuse me? If you can. If I produce a frequency of 800 Hertz, Ali will actually detect, will measure exactly the 800 Hertz. But if I start to move in Ali direction or away from Ali, I will produce the same 800 hertz, but Ali will detect something else. Will detect a frequency that might be higher or lower than the 800. That depends on my velocity. That's going to depend on my velocity and the direction of the motion. Not only the velocity, not only the speed, but also the direction. If I am approaching or receding from Ali. So the frequency will change if the source moves. And same applies. If actually the source is at rest, that's me, and Ali, if he moves into my direction or away from me, Ali will hear the 800 hertz differently. Ali will detect different signal. It's not going to be 800 hertz. It might be higher or lower depending on his direction. How high or how low, that's going to depend on the speed that he moves in with. And if we can, well, I'll explain to you why. And if we carry that a little bit further, if the two, if the source and the observer move relative to each other, if they move at the same time, the observer will hear the sound wave, the frequency of the sound wave differently. It's going to change as well, and that's going to depend on the speeds of the observer and the source. Farida.
Was it the source and the receiver, they're moving in the same direction?
Mm-hmm. We'll see.
Don't change the name.
No, we'll see. That's a very good question. That's a very smart one. Ashur? Yes, ask. Ask. Ask.
He was asking what's the physical unit for it, and that's also this.
What is the
unit for the sound?
Oh, for the intensity? For the intensity, that's watt, because it's power divided by area, it's watt per meter square. But for the sound level, it's decibel, dB, that's dB, that's dB, decibel. For the sound level. Good, nice. Okay, why? Why does that phenomena happen? Nada. This is the first case. I have the source that's at rest, and the observer is approaching this. Okay. What happens in that case? When the observer moves, I'm going to assume that the speed of the sound is v. That's the speed of the sound. The frequency that's produced by the source is f. And the wavelength is lambda. What is the wavelength? What's the frequency? I want to actually... Yes. Okay. There's a relation that relates the velocity of the sound, the frequency and the wavelengths. It says that the velocity of any wave equals to the frequency times the wavelengths. Times the wavelengths. Velocity of the wave equals the frequency times the wavelengths. If I draw the relation between amplitude and time, you get this. This is the wave. Okay? This is one complete wave. This is one complete wave. Oh no, any wave will look like that. Amplitude will change with the time as a sine wave or as a cosine wave. Usually we represent it as a sine wave. So that's one complete wave. This distance here we call periodic time. That's periodic time. This is the time it takes for the wave, for one complete wave. That's periodic time. 1 over the periodic time will give us the frequency of that wave. How many complete wave in 1 second? That's the frequency of the wave. But if you draw the amplitude as a function of x, as a function of the distance, that's what you get. Again, sine wave. that distance, we call that one complete wave. This distance, it's lambda, the wavelength. It's the length of one complete wave. It's a wavelength. And there is a relation between frequency, wavelength, and the velocity. Velocity equal to force times the lambda, times the wavelength. In here, in that equation, I'm going to explain only once. I'm not going to ask you why the explanation for the rest in the exam, but I want to explain to you once why, if one of them, the source or the observer, moves, the wave change. What happens here is when the observer moves into the direction, observer moves into the direction of the source, the speed of the wave relative to the observer increases. So if Ali moves into my direction, he will see as if the wave is propagating into his direction faster. It's the addition of the velocity of the wave plus Ali's velocities. Right? So now the velocity of the wave will look different. It's V, the velocity of the wave as originated from the source, plus the velocity of the observer. O stands for observer, actually. So if the velocity change and lambda is the same, does not change, then the frequency that will be detected by the observer is going to be different. Actually, after some mathematics, which I'm going to ignore because the semester is very short, this is what we got. That's what we prove. If the observer moves and if it approaches the source, then the frequency detected by the observer equals to the velocity of the wave plus the velocity of the observer divided by the velocity of the wave times the frequency as it comes out from the source. Again, the frequency as detected by the observer equals to the velocity of the wave plus the velocity of the observer divided by the velocity of the wave times f. What happens to the frequency? It increases. Yeah. We'll go there. Don't just rush into it. So if the source, if Ali approaches me, we apply that equation. If Ali recedes from me, if he goes away in the other direction, that's what happens. Because simply the velocity, that VO, reverse direction. So now, if the observer moves, we apply either that equation or that equation according to the direction of the motion of the observer. Good. Wait. Now, if Ali is at rest, if the observer is at rest, and I move, and the source moves, that's what happens. If the source approaches the observer, if I move in Ali's direction, then the frequency that Ali will hear, the observer will detect, equal to the velocity of the wave divided by the velocity of the wave minus the velocity of the source. S is for the source, the velocity of the source times F. What happens to the frequency? It increases. This ratio is going to be more than 1. It increases. But if I go away from Ali, if I move in the other direction, the frequency will decrease. So for the same phenomena, we have 4 equations. And this is very confusing. It's really hard to actually differentiate between them. The only way to differentiate between them is to prove each one of them. And guys, because this is a very short semester, I'm going to save you that headache. I'm going to explain to you a little bit different way. I'm going to combine the whole equations, 4 equations, in only one equation. This is the general equation. So whatever the observer move or the source move, we're going to use that equation, and I want you to pay attention to that because this is very important. Wait, let me finish, then I will take all the questions later on. If the velocity of any of the source, if the source or the observer approach each other will take its velocity to be positive. Keep that in mind. If the source or the observer recede from each other, their velocity will take it to be negative. And this is the law. This is the general one. Those signs do not change. They stay the same. So now let's assume that the source and the observer are at rest. So it's V plus 0 divided by V minus 0, which is V divided by V. Whatever you produce, the observer hears. Now let's assume that the source is at rest. Vs equal to 0. And the observer approach the source. So the law is going to be F prime will equal to V plus V0 times F. Then we get the law, which is the first one that we have explained today. Let's assume that the observer recedes. He goes away in the other direction. Then it's actually F prime equal to V plus negative V0 divided by V minus 0. Then it's V minus V0 divided by V. You don't have to write this. Just remember what I do. Okay, guys? Now let's assume that the observer is at rest. And the source approach, Sharif, and the source approach the observer. Observer is at rest, then it's V plus 0 divided by V minus plus Vs, because that's approach. So it's going to be V minus Vs. And if the source recedes, this is going to be negative, it's going to be plus. And if the two of them move, apply the same rules. Now back to your question when you said, assume that Ali runs in that direction by a velocity V, O, and I run after him by the same velocity. So V0 equal to Vs. So what I do? Ali recedes from me, because he runs away from me, and I approach him. It's going to be plus V0 minus, plus minus V0, which is going to be minus, and it's going to be minus plus, it's going to be minus. So it's going to be minus. The same quantity. So that ratio is going to be 1. And that makes sense. It makes lots of sense. If I run after Ali with the same velocity, not as if no one of us is moving. Our velocity relative to each other is 0. Okay? And that makes sense. Amira? Very nice, very nice. This is a very smart question in here. All what I'm assuming is we are moving along the same lines. So far, I'm moving along the same lines. So if Amir is right there and I move in that direction, then what should I do? Then you resolve the velocity into two components. One along that direction and one along the perpendicular direction. And this one is the one that you put in the formula. I'll say it again. Amir is saying, okay, you're talking so far about the source and the observer are moving along the same line. They're doing this. But let's assume that the observer is at rest. That's Amira. And I'm here, but I'm not moving in the direction of Amira. I'm moving along that direction. So what will be the frequency then? How can we calculate the frequency that the observer hears then? What I'm saying is, now this is my velocity. You have to resolve that into two components, one along that direction and one along the perpendicular direction, that direction. The one that we put in that equation, the one that we put in that equation is this one. That component along that line. No. There will be a change, of course.
So we're talking about this second, this particular second.
Yeah, so, see? Ali actually he said that means that, but if you do this, the angle will change, this velocity component will change. So actually each time I move that way, the frequency will change because the velocity changes all the time.
It's only the velocity, not the angle. You don't have to resolve it, right?
You only resolve the velocity of the source in that case, of the source. So because the velocity is along that direction, and whatever we put here as VO or VS is the velocity along the direction, along the line between the source and the observer. So if I move in that direction, you have to resolve that velocity into two components. One along that line, and one along the perpendicular line. The one that along the perpendicular line we're not going to actually look at it at all. This is the one that's going to be of our concern.
So we should first know our direction, the x and y direction.
Yeah. Yeah.
But it is impossible to know because
Now, actually, at that location, you'll hear a frequency. When I move that way, you'll hear a different frequency because obviously that component has changed. When I move that here, you're going to hear the same frequency.
If someone's moving
You're gonna-
x-axis, then we move our y.
Same thing. If Amira moves that way, and I move that way,
The resolution is there.
yeah, it's going to be a complicated problem, but it's the same concept. You always have to find this velocity. You have to find that velocity, the velocity between the source along the line of sight. The velocity along the line of sight, which is the velocity along the line between the source and the observer. This is what you want.
why is when you are here it should be
Because my velocity, all of my velocity is along that direction, and the velocity along that component is 0. So yes, because you are at rest, observer V0 is 0, and my velocity along that direction is 0. So you hear whatever I produce. At that location, at that specific location, if I move in that direction, Amira will hear exactly whatever the source produce. Simply because she's at rest, so V0 is 0. I'm moving along that direction. My velocity relative to her in that direction is 0. So Vs is 0.
But you're getting further away.
Oh, but when I do this, now the component, that velocity has two components, one here and one here.
but you think that
Every time you repeat that.
Yeah, of course. So that's why you find, exactly like Ashur said, you find the frequency at a specific point of time. And if that change, the frequency will change. And if that change, the frequency will change. So if I ask you to do this, I will ask you to do it at a specific point of time. What is the application of that? Radar. So every time you get a ticket, because you're speeding, this is exactly what they do. They have a gun that produces a wave, where that wave hits your car and goes back. And according to the velocity of your car, they actually they send a specific frequency, and they measure the reflected frequency, and from that, with the simple calculation, they can find the velocity of your car. They calculate the velocity of your car. And that's how you get ticket. Radar for airplanes, they use the same concept. When they measure the flow of your blood in your body, they measure the same concept. And when they measure the heartbeats of the baby inside the mother belly, they also use the same concept. And there is a problem in the assignment about this.
why the heartbeat
No, it moves. The heart beats. So if you have a source here, the heart moves closer and further away from the source. So actually it moves. It's as if you have an observer that moves or a source that moves. Okay, guys, thanks so much for coming. We have an exam.